And a reminder about the thermodynamics of these concepts: when you have delta G gives free energy as a negative number, the reaction is spontaneous. When delta G is a positive number, more than 0, the reaction is non-spontaneous. You need to do something for the reaction to happen. And when delta G is 0, we say the reaction is an equilibrium, it's on a standstill. The forward rate and the reverse rate are the same, and the concentration of reagents and products remain constant. It's kind of frozen in time, reacting backwards and forwards at the same speed. So you end up with a particular concentration of each of the reagents and products. And that's it. Or is it? Is that it? We have a certain amount of reagents and products, and there's nothing we can do about it. That's what we're going to get. Well, the answer is no. We can disturb this equilibrium. We can try to get the reaction out of this equilibrium, this forward rate equals reverse rate standstill that it has reached. It will evolve back to go back to an equilibrium state, but in the process, if we are clever about it, it will give us more product. So there are ways in which you can disturb the equilibrium. The reaction momentarily will leave this equilibrium state. It will work, the reagents and the products will react in a way that it will go back to the equilibrium state. And the equilibrium state will be reached, but with different concentration of the different reagents and products. So what happens if we disturb the equilibrium? Well, if a reaction is at equilibrium, and you do something to perturb that equilibrium, to get it out of the equilibrium, the chemical reaction will do whatever it takes to go back to the equilibrium position, because as a stable one it has reached. So when you apply a stress to a chemical reaction which has reached equilibrium, it will shift in the direction of the products of the reagent that partially relieves that stress and goes back to the equilibrium position. And we call that Le Chatelier's principle, because of the French chemist who proposed this principle. And what is a stress in a chemical reaction? How do you stress a chemical reaction? Well, you can do it in 3 ways. You can change the concentration of one of the reagents or one of the products. You can change the temperature that the reaction takes place, or you can change the pressure of the volume of that reaction. For example, by changing the size of the reaction vessel. One key thing you cannot do, well, you can, but it won't have any effect, is add a catalyst. Catalysts do not affect the equilibrium. Catalysts help a reaction start, providing that alternative pathway with a smaller activation energy. It makes things easier, so it will be faster to reach the equilibrium. But once the reaction is at equilibrium, they have no effect, because the reaction has already started and it has reached and stands still. So the catalyst will not do anything. The catalyst only help you get things started. A reaction at equilibrium has already started. It has progressed, it has reached the point in which the reaction forward and the reaction backward, those two rates are the same. So only concentration, playing with the concentration of reagents and products, playing with the temperature, increasing it or decreasing it, or changes in the pressure or volume, for example, by changing the size of the reaction vessel, will have an effect on that equilibrium. So how will a change in concentration affect the equilibrium? So imagine we have the reaction A plus B to give us the reagent C. And the reaction has reached equilibrium. What will happen if we add more of one of the reagents, A or B? Well, the reaction is at equilibrium. If you add one of the reagents, the reaction will try to react to make product, to make sure that you reach the equilibrium again. So when you add one of the reagents, the reaction will shift right towards the side of the products. And the reaction is at equilibrium. you add one of the reagents, or both, and the reaction is not an equilibrium anymore. So the reaction happens, so again, you reach that equilibrium condition. And what happens if you add a product? Well, in this case, you add the product, the reaction reacts to consume that product to go back to that equilibrium position. So it will shift left. In a way that you make more reagents. And that might sound slightly counterintuitive. Why would you want to make more reagents? And yes, that makes sense in industrial context, for example, but that's how lots of natural processes happen. For example, metabolic pathways, that our bodies, playing with the amount of reagent and product of a particular reaction, is able to regulate how much of the different chemicals involved in that reaction happen. So again, if you add one of the chemicals and that chemical is a reagent, the reaction will react to make more product to consume that reagent until you reach the equilibrium condition. And if what you do is you add a product, then the reaction will shift towards the product, as the reagent side, towards the left, again to consume, in this case, that product and go back to that equilibrium position. The equilibrium constant, the proportion of the reagents to the products, will be the same. What will have changed is the individual concentrations of reagents and products. So overall, the equilibrium constant will not have changed. It's still the same ratio of reagents to products. The equilibrium constant only changes with temperature. But within that equilibrium constant being the same, the individual quantities of reagents and products will be different. And a couple of examples of this, how you can play with concentrations and move the reaction towards the right or towards the left. The phosphate buffer, and I mentioned this in videos related to acid-base chemistry, keeps the pH of mammals' cells at around 6.9, 7.4. And it's very effective at that. And what happens? Well, you have this particular equilibrium, you have dihydrogen phosphate that reacts with water to give you hydrogen ions and hydrogen phosphate anions. So it's in the cellular fluid, and if hydrogen ions enters the cell, so if there are more hydrogen ions because they are entering through the cell walls, then the equilibrium will shift towards, it consumes those hydrogen ions, it will move towards the left. And if you have either more water or perhaps hydroxyl ions that enter the cell, then the equilibrium will move to the right to consume that extra ones that you have added. So this is an example of how you can use in this case an acid-base equilibrium to regulate the amount of hydrogen ions you've got in the cell to keep the pH within particular levels appropriate for the cells. An example of equilibrium in nature is also the carbonate system. For example, to regulate acidity in oceans and seas. If you look at, let's say, for example, they are all equilibrium reactions, and if you think of, for example, of this one, the carbon dioxide gas dissolved and carbon dioxide dissolved in the water, if you have more carbon dioxide in the atmosphere, if there's increase in CO2, then the equilibrium will displace towards the shift towards the formation of products. It will shift, well, right, in this case, down. Or for example, if you're looking at this part of the equilibrium, if you imagine you have more calcium ions in the medium, let's say because you are in a particularly chalky area, then if you have more calcium ions, that means that that part of the equilibrium is one of those chemicals is higher, and the reaction will react to produce, it will shift in this case left for the production of calcium carbonate.